Mathematics is often taught as a tool for calculation, a way to count, measure, and solve. In a governance architecture, it functions as a formal pipeline for transforming raw observation into verified, committed facts. It is the gatekeeper of entry into knowledge. We can call this a proof governance architecture. These are the specific, unyielding rules a system uses to dictate what becomes canon and what remains mere speculation. We see these architectures embedded across history, in the interlocking cyclic ledgers of the Maya, the drift repair schedules of Gaulish timekeepers, the rigorous syllogisms of medieval universities, and the public geometric challenges hung in Edo period Japanese shrines. Every one of these systems faces the same epistemological tension. By what exact mechanism does a perceived pattern earn the right to become an admitted, trusted state? The answer lies in the gates. A pattern must pass through rigid filters of admissibility before it can be accepted. Once accepted, it is subjected to strict state transition rules, defining exactly how data can be manipulated without breaking its integrity. And if a claim bypasses these rules, the system accumulates proof debt, a structural weakness that must be tracked and eventually paid down. These traditions serve as foundational engineering specs for epistemic verification. They provide a structural lineage for the complex data systems we built today. The earliest structural attempts to map the sky involved massive stone megaliths built across rugged landscapes, mapping local horizons to celestial cycles. This visual alignment between ancient stones and celestial bodies is compelling, but a line can be drawn between almost any 2 points. A physical orientation is merely a candidate relation, not proof of builder intent. The challenge is false pattern detection. The mind easily overfits data. To verify intent, we need a statistical control gate, or null model. Would these exact alignments appear by chance? Then, the cultural context gate. Did this specific target actually matter to the builders? This establishes a strict boundary. Visual elegance is not evidence. A beautiful coincidence has no epistemic weight. To move a claim from a hypothesis to a formal proposal, it must survive measurement, pass the null model, and align with historical constraints. Pattern detection is inadmissible without explicit measurement, statistical control, and alternative explanation review. That is the first rule of the architecture. Verification is only the first step. To remain admissible, ancient timekeeping had to function as the active governance of a computable state space. We see this in architectures of interlocking cyclic topologies. The Maya tradition tracks time by locating a single day within multiple synchronized cycles, such as the 260-day Tzolk'in and the 365-day Hab. But any system tracking celestial mechanics faces a mathematical mismatch. A lunar month is not an exact divisor of a solar year. Look at this bronze plate, the Kalingi calendar. It is a material ledger tracking phase drift. As lunar months pull away from solar seasons, the error is explicitly measured. To fix this misalignment, it inserts an intercalary month, an extra block of time, snapping cycles back into phase. The Hebrew and Jewish calendar tradition preserves a parallel dual-cycle governance system, ensuring lunar months stay locked to agricultural seasons so that legal and ritual obligations occur in the correct window. Historically, this began through direct human testimony, witnesses reporting the new moon to a court. Over time, governance transitioned from live observation protocols to rule-based mathematical intercalation, maintaining the same authority through algorithmic calculation. This forces us to redefine system maintenance. In a well-governed architecture, drift is not a failure, it is a predictable variable.
Scheduled repair is the mechanism by which continuous state alignment remains admissible over time. As mathematical governance evolved, the challenge shifted. How do you alter a state without breaking its verified status? Euclid's Elements solved this through deductive admission. Before geometric transition occurs, the system relies on explicitly declared definitions. These postulates function as authorized transition primitives, strictly constraining allowed operations. This strict governance of transition carries directly into Renaissance Europe. Mathematicians like Cardano and Tartaglia pushed algebra forward by mapping out the complex transition rules required to solve cubic equations. This introduces symbolic transformation. By changing the representation of an equation from words to symbols, they could diagnose problem classes and solve hidden variables. But throughout every algebraic operation, a core invariant must survive. The underlying equality must be preserved, even as the surface changes. This establishes the condition for state transformation. You can only change a state's representation if you do not lose its original identity in the process, and you must leave a mathematically traceable path from the initial problem state all the way down to the final solution state. A transformation is inadmissible unless it explicitly preserves the governing constraint of the system. What happens when a claim is made public, but the transformation path is left out? During the Edo period, Japanese mathematicians developed a public receipt culture, painting complex theorems on wooden sangaku tablets and offering them at shrines and temples. These artifacts are beautiful, but they intentionally decouple the mathematical claim from its underlying proof path. The answer is displayed, but the derivation is absent. This creates proof debt. The theorem is publicly stated, but the logical steps required to verify it are missing from the artifact itself. Public acceptance of a physical artifact or a published paper can mask an entirely unresolved dependency graph beneath the surface. To counteract this kind of proof debt, medieval scholastic universities built institutional models designed to stress-test reasoning before it could be certified. Students progressed through the liberal arts quadrivium, where Aristotelian logic acted as a gatekeeper, preventing faulty inferences from passing as truth. Claims were subjected to adversarial disputation. A proposed theorem had to survive structured objections, precise distinctions, and formal replies before it could earn institutional certification. This enforced the use of strict claim status labels. A system must separate an unsupported opinion from a plausible argument and distinguish a probable theory from a verified demonstration. A published artifact is merely a proposal carrying proof debt until its dependency graph is fully resolved by institutional or logical governance. We can synthesize these historical architectures into a single pipeline for modern systems, the claim status lattice. Raw observation enters the system. It must pass the null model gate to strip away false patterns. It passes the drift repair gate, ensuring temporal state alignment. It moves through authorized algebraic transformations, preserving its underlying invariant constraint. Finally, it clears the scholastic gate, paying down its proof debt and resolving its dependency graph to emerge as a verified admissible receipt. This pipeline highlights the structural challenges shared by ancient systems and modern information architecture. Black box AI models and distributed databases require similar gates to manage uncertainty and resolve dependencies. Architectural rigor demands that we build systems that don't merely calculate answers, but programmatically verify their epistemic right to exist.